This video is about the Beolover SyncDrive, a brushless synchronous platter motor for Beogram 4002 and 4004. It replaces the DC platter motors in late model Beograms. For more information, please visit our blog at beolover.blogspot.com. For purchase, please go to our store at beolover.com. So why would you make the effort to replace your original DC motor with a Beolover SyncDrive? Now typically when I restore a Beogram or people send me their DC motors and I measure them, before I restore them, then over 24 hours I often see RPM profiles like this here. So you see it's anything but constant, the RPM, and we also get these really significant drops for many of these motors. This is all a result of dry motor bearings, and in some of these motors also bad spark snubbers that are mounted on those little rotors. Now when I restore these motors by reinfusing the bearings and sometimes replacing the spark snubbers, then I typically get something like this here, and this is really one of the better results that I ever measured. And so in this best case scenario, we basically have a RPM stability that varies over 24 hours considerably, mainly because of temperature changes. So these are analog control systems, so they depend on temperature and other environmental factors. Now the Beolover SyncDrive, because it is based on a digital control system and it's also run synchronously, so it doesn't have a feedback mechanism, and more about this later in the video, we get a very constant RPM behavior. In essence, the Beolover SyncDrive probably brings these DC motor Beograms up to the level of the later 8000 and 8002 models. So if you care about the performance of your Beogram, then I think it makes sense considering putting in the SyncDrive. It's also very easy to install. All you have to do is remove the original motor by removing these screws, taking it out, bolting in the SyncDrive, and then connecting it with this red wiring harness to the main PCB. I'll show that in a little while in this video. So it's a very simple transformation, and it really brings your DC motor Beogram up to a new level. So in the remaining part of this video, I will give a brief introduction about the SyncDrive. I will show you how to install it. I will give a demonstration mainly of the user interface, and then in the end of the video I will discuss the performance in some detail and how the SyncDrive compares to other Beogram editions. Let's do it! This here shows the components of the SyncDrive system. It's essentially a plug-and-play replacement of the original DC motor. So this component here bolts into the mounting posts of the original DC motor with these screws and these isolation washers here, and then you connect it to the main board using this main PCB adapter and this red wire harness that plugs here into the SyncDrive board. So this means it's a very easy installation without any soldering or other necessity for modifications of the Beogram. Once installed, it has exactly the same functionality like the original motors, so once the aluminum panels are back on, you will not notice a difference relative to the DC motors. You can still use the keypad, change the RPM, etc. It's also compatible with the standard belt, so even though it has this bigger pulley, you can use the standard belt that you have in your Beogram. It can also be combined with other Beolover upgrades like the Commander remote system and the RIAA internal preamp boards that are available for the DC motor Beograms. Let's have a quick look at the SyncDrive features. Let's start with the connector to the main PCB. That's where you plug in that red wiring harness that I just showed. Over here we have a speed sensor that allows the SyncDrive to measure the platter speed. Here we have the brushless synchronous motor at the heart of the system. This here is the microcontroller that controls everything. Down here we have the user interface. The user interface has 4 buttons, 2 of them allow to manually change the RPM. Then this button here controls the auto RPM calibration feature, and the 4th button allows to turn the RPM panel above the keypad on and off. So basically you can disable the RPM panel, and that ensures that the Beogram always runs at the correct RPM. Let me explain real quick how a brushless permanent magnet motor works. So the word already says here, brushless means we don't have any brushes that bring current to the rotor. And the reason for that is the rotor is made from a permanent magnet, so there is no need for current flow on the rotor. So how does this rotor gets to turn? Well, for that we have those static coils that are mounted to the stator. And all we have to do now is apply current in sequence to these 3 coils, and that will pull that rotor around, right? So if we turn on this coil here, then the rotor will align with it. And then we turn this one off, we turn this one on, and the rotor would move another 120 degrees over here and align with this coil, and then we fire up this one and it would complete the rotation, and then we just do this in sequence. So this is what you see here. So a very primitive brushless permanent magnet motor could be run by these current pulses, and that would cause the rotor to rotate. But you can imagine that this here is probably a little bit rough, right? So the motor would make a lot of noise and the motion wouldn't be very smooth. So that's not what we want in a turntable, of course, because there we want a motor that runs super constant and with very little noise and choppiness. And that brings us to the synchronous brushless motor. And so here we simply replace the pulsed current pattern that we just saw with smooth sine waves that are 120 degrees phase shifted. So you see that here these 3 phases now turn from these pulses into these smooth sine waves. And each wave is 120 degrees shifted to the others. And that gives us basically a smoothly rotating magnetic field. So it just rotates here nice and smooth around 360. And this permanent magnet now just follows this field vector. And we get a very nice and smooth motion which has an almost constant torque. And so that gives us a very low vibration motor that is perfect for a turntable. Another great thing about this is if we have a way to make these sine waves with a very constant frequency, so if we have a very precise oscillator, then this motor will have a very constant RPM, right? Because the permanent magnet simply follows these sine waves, and it's completely in phase. And so that's why we call this motor a synchronous motor, because it is in sync with the frequency of these sine waves. So that's a very perfect motor for a turntable. In fact, this is the very principle that is used in the initial version of the Beogram 4002 and the Beogram 4000. There we have synchronous motors that work with 2 phases, and the sine waves are generated by an analog oscillator. And now it's time to show you how to install the SyncDrive. The first step is to take out the original motor. And now we take out these 3 plugs from the main board. this one here we need to put out of the way, so we can plug in the little adapter into this jack, and the plug that was in here now goes into this adapter, like so. Same orientation, right? Blue on blue. And now we can plug back the other plugs. Make sure that the red harness is under the plugs so it stays out of the way when the turntable is running. Just feed it around the platter bearing and under the power wires. And now it's time to bolt in the motor. The SyncDrive, it bolts to those two posts where the original motor was bolted to. You see the mounting holes, they line up exactly. And now we bolt it in with the provided sheet metal screws. Make sure that the damping washers are under the metal washer when you bolt that in. The final step is to plug in the red harness, and so you see that these plugs are polarized, these little plugs, and so here you see the contact terminals shine through on this side, while the other side is completely blank, white, and so this is how we want to plug it in. If you do this the other way around, it's actually possible to damage the little contact terminals that are in these sockets, because these plugs are pretty small. So please make sure that it's lined up like this, and then you can put it in here and plug it in. So it's important that it's all the way in. That means that these little features here touch the socket that's on the board. And that basically completes the installation. Finally, we can put the sub-platter back in and put the belt around, and you do that exactly the same way like you would with the original motor. So with the left hand you feed it around the pulley, and with the right hand you drag it around the sub-platter, and that's it. By the way, the belt stays on this pulley even though it doesn't have guards, because it has a crown. So that means it's a little it has a bulge here, and so that keeps the belt centered on the pulley. Now we can put in the main platter, and this is pretty much all that's needed. It should run now pretty close to 33.33 RPM, but I will show you in the next segment how to perform an auto calibration that it will be precisely at 33.33, because the sub-platters and these pulleys here, they all have certain manufacturing tolerances, and so there may be some minor deviations from the nominal 33.33 after installation. So it's good to do an auto cal when you put this in for the first time. But this is essentially it. The SyncDrive is now installed and ready to go. Now it's time to give you a quick demonstration of the features of the user interface of the SyncDrive. So this is the user interface. By pressing any of those four buttons, it is activated, and that's then indicated by this blue LED. So when the LED is on, then the interface is ready to interact. So this button here allows to activate and deactivate the RPM panel that is above the keypad of the Beogram. When the panel is in the loop, then the LED is on here. This button is for auto calibration of the RPM. So just press it, and then after 2 minutes the RPM has been calibrated for 33 or 44. And these two buttons, they allow a manual adjustment of the RPM. The two LEDs here, they indicate whether the platter is too slow or too fast, exceeding 0.2% of the nominal speed, 33.33 or 45. I should point out that these settings are independent for the two speeds of the Beogram. So when it runs at 33.33, then everything here applies to 33.33. When it runs at 45 RPM, then the RPM settings apply for 45. This means that the calibration or manually set RPM are saved independently for each of the speeds. So just switch it between the two RPMs and then do the RPM calibration or setting as you like it. So let me show you now how to do this. I'm gonna show this for 33 RPM. So for doing this, first start the turntable at 33.33. So the platter basically needs to be running, and then we can start do the adjustments. The first step is to activate the user interface, and that you can do by pressing any of these 4 buttons. So after pressing, you see here that the blue LED is on, and we also see that the RPM panel is active because this LED is on. And I just realized that we cannot see the labels on these buttons from this perspective. So this here is the button that controls the RPM panel, this here is the auto calibration button, and these two here are plus and minus for changing the platter speed manually. So let's let me walk you through the functions. So first, let's change the RPM manually, and we see here the Beolover RPM device is hooked up. And so you see here now when I press the minus button, the RPM slowly changes here to the slower. And if you press it often enough, then the LED comes on here indicating that you're too slow. It comes on at 0.2% deviation, and the same with the plus button. So we're getting a little faster here, and then the LED is on when you're far enough away from the nominal speed. So if you want to recover to nominal speed, you can simply press the auto cal button. And you see here now how the time accelerates. So I ramped up the speed a little bit of this video clip. It takes 2 minutes, and then after 2 minutes the LEDs go off, and then the calibration is back in check. So you can of course also change the RPM by using the built-in trimmers above the keypad. So I'm showing here the 33 RPM trimmer. So currently it's at 0. So the way I programmed it is that you have to go beyond plus 0.5 or minus 0.5 in order to affect the change. I did that to ensure that if you're close to 0, that the SyncDrive knows that you want the nominal speed. The reason for this is that these old potentiometers that are in this panel, they sometimes have have values that deviate, and so when the SyncDrive reads it out, then there could be misunderstandings. So this is why I said, okay, plus minus 0.5 here means that we are at 33.33, and if we go beyond, then we get the change. And rest assured, you get the change that is spec'd here in the user manual. So this dial here is supposed to do plus minus 3%. And so this is what you get between here and there, minus 3%, and between here and the end of the scale, plus 3% approximately. Okay, so let's demonstrate this. So I turn on the panel. And now you see here, when I go beyond 0.5, the RPM here is accelerating. And so now you can deactivate the influence of this RPM panel by simply pressing the button here again, and you see now the panel is not active anymore, and so we're going back to the nominal 33.33 speed. And if you turn the panel back on, then it'll go back to the 33.8 that we adjusted previously. And now we're coming to the final part of this video, the discussion of the performance of the SyncDrive. First, I will review a little bit the measurement techniques that have been used traditionally and compare that with the Beolover RPM device that I'm using. And then I will compare the SyncDrive data to other Beograms from this period. And so we see how the SyncDrive measures up. Let's first have a look what Bang & Olufsen published for the Beogram 4002 with DC motor back in the 1970s. So in the service manual there is a list of specifications, and here we find 2 wow and flutter entries according to DIN and WRMS. And then here an entry for speed deviation and speed control range. So the speed control range, I believe, is just the RPM adjustment range on the RPM panel above the keypad. Now, speed deviation probably refers to long-term RPM stability, while wow and flutter, that is a measurement traditionally of RPM changes that are repetitive and occur at certain frequencies. And so I looked it up on Wikipedia. Wow appears to be speed variations below 4 Hz and flutter above 4 Hz. 4 Hz seems to be the most sensitive range of the human ear for recognizing such RPM fluctuations. And that brings us to the weighing of these measurements. So we have here different numbers, and there are several more standards that were used or are used. And in these different measurement standards, different weighing curves are being applied to RPM fluctuations that occur at different frequencies. And so here, this is that human 4 Hz center, where it's most important to have stability, and then if we go away from this 4 Hz frequency, it's less important to have RPM stability there. And so that's what they try to accommodate with these weighing curves. Unfortunately, there are several out there, and so this gives us these different numbers, and that makes it difficult to compare different Beograms and other turntables with each other. I looked a little bit into how these measurements were performed back then. At the center of the measurements was a so-called wow and flutter meter, and this meter basically was used together with a test record that had a test tone on it that typically was at 3.15 kilohertz. So this record was played on the turntable, and then the sound was fed, the signal was fed into the wow and flutter meter, possibly through an amplifier. And then in the wow and flutter meter there was basically a frequency discriminator that turns deviations from a certain center frequency into a voltage. And this voltage was essentially displayed on the meter here, which is a voltmeter, but it was of course calibrated as a wow and flutter percentage. When it comes to issues and limitations of this type of measurement, then of course the test record comes to mind immediately. If the test record isn't made very precisely, imagine for example if the center hole isn't exactly in the center, then the test record already has a built-in wow and flutter. Another limitation is that long-term measurements are pretty much impossible with this technique, because the test tone is limited to the length of one side of a record, which probably is 30 minutes or so, and the other is to store the measurement. The only thing that comes to my mind is that one could have used a paper plotter and basically plot the voltage over time on this sheet of paper that is being fed through the plotter. Now, I don't have a wow and flutter meter from the 1970s, so I a while ago developed the Beolover RPM device, which recently enjoyed an update. And this device basically takes advantage of the unique platter shape of Beograms, namely that they have these black ribs. And so what the Beolover RPM does is it simply holds a sensor above the platter as it spins, and it measures the time between these ribs passing under the sensor, and it calculates the RPM from that. So the sensor works fairly simple. It has an infrared LED that sends light to the platter, and the shiny areas between the ribs, they reflect the IR very well, while the ribs not so much. And so we get a intensity pattern like this. Every time a rib passes under the sensor, the light intensity that it measures in its IR diode gets low, and so from this here it can calculate the RPM. So 75 milliseconds between ribs corresponds to a speed of 33 RPM. This is how the Beolover RPM looks in the flesh. You just put it next to the spinning platter with the red indicator pointing towards the center pin, and then you can measure the RPM. The Beolover RPM is available to other Bang & Olufsen aficionados through the Beolover store. The RPM has two measurement modes. One is labeled fast and the other slow, and so in fast mode you basically get the raw data. So each time a platter rib passes, you get a data point. In the slow mode, it gives you a reading every 10 seconds, and that is the mode that you would want to use to measure the long-term RPM performance of your Beogram. So in the next few slides, I'm gonna use both of these modes in order to characterize the performance of the SyncDrive and compare it with the other Beogram motors. Let's first look into a direct comparison between the SyncDrive and the original DC motor. So these two measurements here, they were performed in the fast mode with the Beolover RPM, and they were performed in the same Beogram. So everything the same, just the motors exchanged. The red curve is the measurement with the SyncDrive, while the blue measurement is the measurement that was performed with the original DC motor, which was restored. So a best condition original DC motor, so to speak. Now the time that is covered here in this graph is about 60 turns of the platter. So this is a measurement that spans about 120 seconds, right? Because it takes about a couple seconds that the platter rotates at 33 RPM. So this strange pattern that you see here, this repetitive pattern, and I will discuss this a little bit more a couple slides down here in this video, that is an artifact of the measurement and comes from slight manufacturing imprecisions of the Beogram platters, namely slight differences in the spacing between the ribs. And if you look very closely here, you see that these patterns basically repeat. They have the same peaks in them, and so this means that every platter has basically a signature. You see the same pattern here in this measurement, which was of course performed with the same platter. But more about this in a couple slides. But what we see here already is that the original DC motor, because it is feedback controlled, it has this pretty strong change of the RPM that actually changes about in a rhythm that coincides with the rotation of the platter. So we have basically a 0.5 Hertz wow that is built in just because this motor is run with a analog feedback control system. The SyncDrive, on the other hand, is much more constant because it doesn't use a feedback mechanism. And essentially, as I explained earlier, the rotor just follows a precisely generated sine wave. We still have a little bit of a pattern in here, which I believe is basically a result of the soft coupling between the motor and the platter by means of a rubber belt. But there is no question that the SyncDrive is intrinsically much better than the original DC motor. On this slide I want to compare the two measurements from the previous slide down here with measurements performed on other Beograms. So this here, the pink one, that was measured on a Beogram 4000 that I recently restored, which has a AC motor, a synchronously driven can stack motor, and it also has a different platter than these later 4002s, which is much heavier. But you see here that the measurement is pretty similar to the measurement that I did with the Beolover SyncDrive. So we can say the SyncDrive basically makes the DC motor Beograms as good as the original Beogram 4000, which is already a pretty nice achievement. The two green curves here, they were measured on a Beogram 8000 and a Beogram 8002. So these are much more modern turntable designs from the 80s, and they have a linear direct drive which is digitally feedback controlled. They are distinguished by the different platters they have. So the 8000 still uses the same style platter like the late 4002, while the 8002 had a etched platter, and we see that in this different pattern that the platterns produce. But overall, these turntables also are very constant, and they have very small fluctuations beyond this platter pattern. Thanks goes here to Sonavor, who provided these two measurements when he tried out my redesigned Beolover RPM device. I tried to evaluate wow and flutter of the DC motor Beogram from these measurements, and so my approach was to simply subtract the platter pattern that we measure on these less wow affected Beogram drives from the amplitude that I measured on the DC motor. And so when we do that, we end up with basically this red change, which would be the wow and flutter component of this measurement. And so if one compares the amplitude here with the 33.33 center frequency, then one comes up with about a wow and flutter number of 0.1%. So that's a little higher than what Bang & Olufsen writes in their specifications, but we need to keep in mind here that the measurement methods are entirely different. So I would say we're probably pretty close. Finally, from the frequency of that superimposed beat pattern that we see here on this original DC motor measurement, from this beating wavelength, which corresponds to about 19 rotations of the platter, we can estimate that the frequency of that wow is about 0.5 Hertz, pretty close to the actual platter rotation, right? It takes about 2 seconds for the platter to rotate, so it rotates at a 0.5 Hertz frequency. So every time the platter turns, it gets a little faster and a little slower on the original DC motor Beogram. And finally, I want to discuss the platter patterns a little bit more. So on the next slide, we'll see this section here magnified. This magnification clearly shows that all measurements have a repeating pattern. And so if you count the measurement points, you see that each of these patterns repeats every 24 measurements, which just corresponds, of course, with the 24 platter ribs that we have on a Beogram platter. It's nice to recognize that all these patterns are different except these two below here, because they were measured with the same platter in the same Beogram. One big difference is the pattern of the 8002 and the other ones, and the earlier ones. The 8002 platter was made by etching, while these here feature stamped slots in the aluminum, into which then the rubber ribs were pressed. Here we have an etched and printed pattern. And so because of this different manufacturing process, we have a much more smooth variation of the rib spacing around the platter. And here we are on the last slide of this video. So here, in difference to the previous performance data, these measurements were done over 24 hours. So this ran an entire day. And here I'm comparing again the Beogram 4002 with the original brush DC motor, the same Beogram with the SyncDrive installed, and I also show here the performance of the Beogram 4000. Unfortunately, this kind of data is more difficult to achieve on the 8002 and 8000 models, because they shut down after 30 minutes when they recognize that no record is being played. So we have to investigate that on a later day. For now, let's just compare the SyncDrive with the analog motors. In both cases, it turns out that the brush DC motor and the synchronous AC motor of the 4000 have actually a very similar drift over time, mainly due to temperature changes, I would assume. And I tried to estimate the change, and I came up with about here 0.12% over 24 hours. Now the SyncDrive, it looks much better, but it also has a little bit of change here over time. And so here my estimation is that it is maybe half the drift that the original motors have. So I estimate here 0.045%. And this concludes my presentation about the Beolover SyncDrive. I hope I was able to show you that it is a great upgrade for any DC motor Beogram 4002 and 4004. Thanks for watching.